one. This one here is literally just this formula that is, if you add up all the degrees of all the vertices in your graph, you should get the number that is twice the number of edges in your graph. Please note both degrees as well as the number of vertices and the number of edges should always be an integer. If you ever start getting into one of these formulas and somehow get a number like, I don't know, 17 over 2, you did something wrong. Or whatever you're trying to do doesn't actually work because you're not allowed to have like 17 and a half edges. Okay? So you watch out for those type of things. The last time we did a baby example where we had a little itty bitty graph here with 4 vertices and 4 edges. We looked to see that the degrees of all of these, there were 2 odd degrees, 2 even degrees, but we added them all up and the total degree was 8, and we saw that was twice the number of edges, which was 4. And we'd looked at that previously because you guys had actually noticed that when we were looking at a quick way of actually counting how many edges were in a graph previously to now, we actually alluded to this formula. Now, we also had a corollary to that theorem, and that corollary was what we ended on last time, and it said if you're in a graph, specifically again, a simple graph, so no directed edges, no multi-edges, the number of vertices with odd degree is even. This is exactly a result of this thing right here. So if you add up all of your degrees, what has to happen? You have to have an even number. Well, if you sum up a bunch of odd degrees, the only way it's going to be even is if you have an even number of those odd numbers. Okay? Otherwise, you actually get an odd number. And we actually walked through this, and I went ahead and showed you the way that I had thought about it in sort of vague, hand-wavy outline, and one of you actually showed a different way, which also would have worked. Okay? So that was where we ended last time. Now, moving on from there is where we actually have some examples. Okay? So the first example that we've got here is how would you actually use that formula, essentially? I guess I shouldn't say it that way. An example on how to use the formula. Don't put it as a question. Okay? So here we've got, suppose we want to construct or we want to draw or we want to build some graph. We want the graph to have 9 edges, and we want every vertex in that graph to have degree 3. So in order to make that work, the question, of course, is, well, how many vertices do we actually need to put into this graph? Okay? Because remember, your graph is comprised of 2 things, your vertices as well as your edges. Now, I'm not actually going to try to draw this graph, but I am going to look and actually answer the question here that says, well, how many vertices do we have to have? So the first thing here is let's go ahead and write down the stuff that we know. Let's make sure this works. So here's what we're going to want to use. That's definitely not what I wanted. Okay. Just a second. It looks like I am not selected. Go away. There we are. I just was clicking on the wrong thing. All right. So what we're going to want to use here is we're going to want to use that formula from Theorem 1. Okay? So to remind ourselves, that formula from Theorem 1 said sum up all the degrees from all your vertices, and it's supposed to be 2 times the number of edges, since it's now off the top of the screen there. Okay? Here's what we also know. We know that the number of edges that we want is 9, because it's actually given here. We're also told that the degree of each of our vertices is supposed to be 3, and that is for all of our vertices. Okay? So that's the information that we have to start with. Now, quick check before I go forward. Are you guys comfortable with this symbol after the comma? Well, I guess string of symbols. There's technically 4 of them there. Does anybody want me to go over what that said? Or when I read it out as I was writing it, was it good enough? Okay, that's what I wanted to make sure, because in terms of the prereqs for this course, there's nothing that says that you guys know what that means. So here's how it's read. This here goes as follows. The very, very first symbol that looks like an upside down capital A, or somebody really messed up drawing a V. This first symbol right here means for all or for any. It actually, you can read it either way. So let me actually title this. That means for, there's an F there, for all. Now the V here, the little v, means any vertex, so any v in, this symbol here means in, and we've been calling our set of vertices capital V, in the set of vertices capital V. And this is under the assumption here, which I totally should have written inside of this example, that our graph G has a set of vertices and a set of edges. So that capital V is talking about the set of vertices. So this literally says, I need degree 3 for all of the vertices that we have. So that's just shorthand notation for doing that. Actually, it's very, very formal math/logic notation for it. But it is, if you don't know what it means, it just looks like gobbledygook. All right, now let's put this all together. We know that if we're supposed to add up all of the degrees from all of our vertices, it's supposed to be 2 times the number of edges. Well, let's actually write that out, and let me not do orange anymore. So I'm going to say, all right, well, we have this sum of the degrees from all of our vertices. Notice the same symbols below the sigma here. This says we're going to look at these of one of our vertices. It's supposed to be 2 times the number of edges. Well, we know what some of that stuff is. Okay? One of the things that we know is we know that on this side, we're going to have the sum. Wow, that was a terrible sum. I'm just going to go with it. And the degree of each of those vertices is 3. Now, do we know how many vertices we have? Nope, that's what we're trying to solve for. So I don't know how many 3's I'm adding up yet, but I do know there's 1 3 coming from each of the degrees for each of the vertices. So that would mean what? That means we have 3 plus 3 plus 3, and the number of them is the same as the number of vertices that we're supposed to have. So this is exactly the same thing as saying 3 times the number of vertices. Okay? So that's all dealing only with the left-hand side. Everybody okay with that logic so far? And remember, the absolute value around that capital V means the number of vertices. All right, not seeing anybody freak out yet. Let's look at the other side. The other side's easy. So when we look at the right-hand side, we have 2 times the number of edges, but we were already told that the number of edges was 9, so we'll just plug it in. So this is telling us that 3 times the number of vertices is supposed to be 18, and as long as we didn't screw up our arithmetic from the previous steps, that would be accurate. Now, what did we care about? We wanted to actually know how many vertices we were supposed to have in this graph, so can we figure out how many vertices are in this graph? What do you guys think? Yeah, now we totally can, and you guys are completely right. As for you, those of you who are sending in answers, this should definitely be 6. Why? Because we just divided both sides by 3 to get that 6. Notice, what did we do here? The key things. We pulled the information from the question. If you've ever dealt with a story problem before, and I'm assuming that all of you have, that's the same thing you always do. The key thing here is we started off by using that classic formula relating the sum of degree to the number of edges. Questions? Make sense? Feeling okay? And that was it for this question. Remember what we wanted. We wanted how many vertices must this graph have? Bam. The answer then would be 6 once we got to the number of vertices. So the next example that we've got, oh, I left myself way extra room there. The next example that we've got is actually almost identical. So for this one, I went ahead. Let me actually pull it up here. For this one here, I went ahead and I copied the exact same thing and then erased the spot that I wanted to change. So the new part here is, or the change is the part in this little bit lighter orange color. I try to make it so that, and I don't know that any of you are because nobody said this, but if any of you have slight colorblind or anything, that you'll be able to see it as a lighter gray, hopefully. But this one here, the only change is, again, we're going to want a graph. We still want to have the 9 edges, but now instead of having all of the vertices of the graph to be degree 3, we only want some of the vertices of the graph to be degree 3. Specifically, only 2 vertices of the graph have degree 3, and everybody else have degree 2. And again, same question at the end, how many vertices in total do we think we're going to have? Now, before we talk about what the answer for this should be, I'm going to throw this question to you guys. Okay? So I'm going to give you a few minutes to think about it. But before we do that, I have a question for you guys. Would you prefer to just think about it on your own, or would you prefer me to throw you guys into groups so you can talk about it together? I've got it set up so we can do it either way. Okay, well that's easier for me, for those of you who've mentioned that. So this question is currently up and activated up on the Poll Everywhere site. I'll go ahead and share it with you. Hopefully that's not too tiny, so I would definitely recommend pulling this up on your own window, either via internet or app. Go ahead, see what you think the answer may be. I realize on the shared screen I've got menu buttons there that are totally covering up some of the statements, which is why I went ahead and kept the second screen over here. But go ahead, take, let's say about 2-3 minutes or so, and see if you've got a guess for how many vertices this graph might have. Yes, the assumption here is that this would be a simple graph. That way, if you want to use that formula that we did in the last example, you can. If it doesn't specify otherwise, the assumption is that it's going to be a simple graph unless somebody tells you differently, is how we actually write things. And the further on in the course you get, the more you'll see that I'll do that. But yeah, simple graph. All right, it looks like most of you have put in an answer, so I'm going to go ahead and hide this screen. If you haven't put in what you think the answer is yet, you want to start doing that soon. All right, it looks like most of you have it now. All right, so while you guys were answering that, I went ahead and started putting the background information out. Okay. So the first thing I did is I wrote out the formula again. That way, if you didn't have it in front of you, you could see it, grab it, use it if you wanted to. And I went ahead and pulled the same information that we had previously from the previous question out. We still knew that we needed 9 edges, so I went ahead and wrote that down. And then I also went ahead and started to pull some of the extra things. We saw that we needed 2 edges that had degree 2, and everybody else had degree 3, and everybody else had degree 2 in terms of the vertices. Now, and that's all I did. Okay. So let us actually go and see what would be a strategic way that's not guessing and checking to see if we can actually figure out how many vertices this graph must have, if it's even possible. Okay. So I'm going to go ahead and do a common strategy, which says, you know what, I don't know how many vertices this graph has, but I'm going to go ahead and say, let's say n of those vertices have degree 2. That way we can actually do a little bit of the arithmetic, do a little bit of the algebra. And at this point, I'm just going to do the exact same thing we did on the previous question. It worked before, hopefully it'll work again. So I went ahead and I'll go ahead and just copy down this same exact formula that says sum up all the degrees equals 2 times the number of edges. Now here's where things get a little bit different. Okay? When we start plugging in the degrees, notice 2 of these guys have degree 3 and the rest of them have degree 2. I'm saying this all crazy. 2 of them have degree 3 and the rest have degree 2. My 2's and 3's were getting messed up. So when we start writing this out, there's the 2 vertices that have degree 3. And then the rest of them have degree 2. So it looks something like that. Okay. Now, when we talked about how many we had, notice the first 2, we have degree 3 times 2 of them. So we can collapse that. And we know that we could totally have just written that as 6. And in the second grouping of the degree 2 vertices, because we went up here and said that there was a total of n of those vertices, I can now say I know I have n terms of the number 2, or n copies of the number 2, and go ahead and write this down as a formula, 2 times n. Now, we can, of course, go back and look at the other side of our formula as well. And let's, instead of writing the symbol for number of edges, let's go ahead and actually write how many edges there were. We said the number of edges was 9, so I'm going to replace the number of edges with the number 9. And this then gets us down to being able to write the 18 like we did before. Okay. So at this stage, we now, once in the simplified form, have 6 plus 2n equals 18. Okay. So what do you guys think? Can we actually solve for n here? Don't know if I think it. Yeah. So we'll go ahead, we'll subtract 6 from both sides, and I'll go ahead and actually give you the middle steps here. Subtract 6 from both sides, we'll get 12, divide 2 on both sides, and we will totally get 6. Now, here is the big fat question. Is 6 the final answer for this question? It is not. So, in this particular case, if we want the total number of vertices in this graph, what do we actually need to do? Because remember, in the last example, we just grabbed the number, actually solved for it. Yeah. So what we're going to do, n here only represents the number of degree 2 vertices. We also need to grab the number of degree 3 vertices. So the total number of vertices is n plus 2, or add those 2 numbers together, as several of you said. You should now get the 6 plus the 2, or a grand total of 8 vertices. Okay. And notice, in terms of procedure, this is identically the same procedure as the last example. The only difference is once you have more than one degree type, there's a little bit of cleanup at the end to go ahead and figure out your total number of vertices. Okay. Questions? Make sense? Feeling kind of okay so far? All right, seeing no questions come in, I am going to scroll us down to the next question that again looks almost identical to the last 2 examples that we've had. There's only one change. Okay. So this one here, again, we're going to assume that we have, somehow I'm missing the letter G for graph. Again, we want to construct a simple graph. We're going to assume that this graph, or we want this graph to have 9 edges. And again, we've got a thing here where we change out the degrees on the vertices. So in this situation, instead of having degree 3 or degree 2 or a combination thereof, we want every single one of these vertices to have degree 5. Now, when we're going about and trying to find the total number of vertices that would live or have to be in this graph, any guesses about procedure? Would we change the procedure in which would we change how we find the number of vertices? Or in other words, what should we do? Hopefully you're all thinking, do something similar to what we've just done. Right? I see people actually jumping ahead from what the question was that I asked, but yes, we're totally going to do something like that. So let me go ahead and write down the information at the top right here. So we'll have the sum of the degrees is supposed to be 2 times number of edges. Let's just go ahead and plug in. So here we're going to have 5 times, well, we're going to have a bunch of 5s. All these degrees would be 5. So 5 times the number of edges that you would have. And on the other side, we'll have 2 times, well, we know the number of edges is supposed to be 9, so write this to the side. And we know that every vertex is supposed to have degree 5. So that's the scratch work to the side. Okay? Now, put that all together. And yes, we'll have exactly what you typed in, which is 5 times the number of vertices is supposed to equal 18. So how many vertices does this formula say that a simple graph would have to have if we have 9 edges and we're trying to get degree 5 on every vertex? Yes. So this would be exactly the same as 18 over 5, which is, I'm not assuming you guys know that off the top of your head, but this guy turns out to be 3.6, which the key thing here is this guy is not an integer. So just as a heads up, that fancy Z right there stands for the set of integers, and that symbol with a slash through it means not a. So that literally, the end part starting at the 3.6, starting here where the cursor is and afterwards says 3.6 is not an integer. So why is it important here that 3.6 is not an integer? What conclusion should we draw, in other words? Yes. So the conclusion here is no graph that has exactly 9 edges and every vertex with degree 5 could ever exist. So here's our conclusion. No such graph, which simply means no graph with those conditions or with those features, no such graph can exist. Now, specifically, this is referring to simple graphs. So if you had something where you were dealing with multi-graphs or maybe directed graphs, maybe this could happen. Again, I didn't look into it, and I'm not going to look into it right now either. But in terms of simple graphs, this would not exist. Okay? Or as one of you said, this graph is impossible. We just can't make it happen. And that's it for that guy. Okay? Questions? Make sense? Feeling kind of comfortable-ish? All right. So moving on. So the next thing feels unrelated, but we'll put it together here in just a second, is essentially the tie-in of some of the things that you can do with this edge counting. Okay? So this is dealing with the component of a graph. I can't remember if I gave you the formal term of this or not yet, but we've definitely dealt with this before. So component of a graph, the component H of some graph is a subgraph of your original graph G right here. It's a very special subgraph. Specifically, it has to be connected. So it's a connected subgraph of G where there's no path between any vertex in that subgraph H and any vertex in the parts of G that are not in H. Now, what does this actually mean? This means it's the biggest possible subgraph that's connected, sort of. Okay? So for example, well, I guess I should write this sort of. So this means, and let me make this a different color so it looks like a complement. So this means that H is as large Wow, large does not have an S in it. Let us fix that. I don't know. I guess we're fixing more than just the S. As large as possible. So here are some examples. So if we look here at these graphs G1, G2, and G3, because I was too lazy to come up with another name. Okay? In graph G1, any guesses how many components we might have in graph G1? Well, there's a lot of subgraphs. In fact, well, there's just tons of them. So you could have the subgraph that's just this line with its two endpoints on the bottom. That would be a connected subgraph. You could have this guy that looks like a triangle right here, but not the top. So those three vertices, those three edges, that would be a connected subgraph. Neither one of these two, either the line at the bottom or the thing that looks like a triangle, would be considered components because both of them would have a path between their vertices to some other vertex in the actual graph. But it turns out, in terms of components, this first graph has exactly one component itself. So there's no proper subgraph. There's no subgraph that's legitimately smaller than your original graph right here that is also a component. Now, that changes when we start looking at G2 and G3. But let me go ahead and write down that conclusion real quick for the first one. Any guesses? Now, go ahead and put in the word connected here, even though you don't need it for component. Any guesses how many components you might have in graph G2? Yep, so in graph G2, you totally have the component, which is just the triangle. It turns out there's one other component, and I see several of you saying there's two of them. Yep, the other component here would be this guy. Notice it doesn't say the subgraph has to be the largest subgraph of your original graph. It's just when you start putting a vertex or an edge in your component subgraph, you keep going until you've got a connected piece. So this is essentially components are saying, hey, if I've got a graph that's disconnected, I'm going to look at all the connected parts of it. Or as we say in graph theory terms, all the connected components of it. This is actually one of the ways to tell if you do have a connected or disconnected graph. Any guesses what you'd look for if you were a connected or disconnected graph? Or maybe I should wait till after a third example here. So hold on to that thought. Any guesses how many components are in our graph G3? Yep, there would be 3. There's this guy that looks like a backwards C, but it's really just a long path. There's also the one that looks just like a single edge with its endpoints. And then there's also this one that has no edges whatsoever. So those of you who guessed 3, you were totally right. Okay? Now, of the 3 graphs, G1, G2, and G3, which one of them are disconnected? Yeah, the last 2. So any guesses if there what a way to figure out if somebody is connected or disconnected might be with respect to the components? And I'll go ahead and box that component on the first one as well. Here, G is connected. Yeah, so that actually is an alternative way to define disconnected graphs. You are a disconnected graph if you have more than one component. Or, alternatively, you are a connected graph exactly when you have one component. So this is one of the ways to look at connected versus disconnected graphs. And why would we throw this in here? We could have talked about it earlier, and we actually did, but I can't remember if we used the buzzword component or not. But notice in each of these guys, whether it's a connected graph or whether it's a disconnected graph, the edge counting formula, where you have the sum of all the vertices equals twice the number of edges, any results that we have for simple connected graphs, and we'll have tons of theorems that talk about you need to be a simple graph or you just need to be a graph, and you also need to be connected. Well, it turns out on disconnected graphs, those properties still work on the individual components. Now, what does that mean for us? That means the sum of the degrees equaling twice the number of edges If it works on this component and it works on this component, well, that means it actually is going to work across the entire disconnected graph as well. But I wanted to throw that out. There's any fact you have that deals with connected graphs, that'll work on any of these individual components of your disconnected graphs too. And one of the reasons that those theorems will often just say connected graphs is because it's easier to prove the theorem, so it's easier to explain why they work in a connected graph, but it'll extrapolate out into these situations as well. So next thing. The next thing is a tie into some bipartite graphs. And here, specifically want to look at, again, some edges with our bipartite graphs. And we actually previewed what we're about to say here the end of last time. So let me not get down to the examples yet. Let me actually write out this. Remember, in terms of our bipartite graph, what was the key thing? And I'm not going to write out the formal definition. I'm just going to remind ourselves of the key things here. The key thing was you had some graph. You had a set of vertices. You had a set of edges. Your set of vertices had to be broken into two subsets, and all edges, actually this is actually getting close to the formal definition, have one of their endpoints in one of those two sets and one of the endpoints in the other edge set. Okay. We also looked at previously that the number of vertices in a bipartite graph, well, I lie. I need to go back to a second. Complete bipartite graph. Complete bipartite graph was all possible edges where your set of vertices, one of them had n vertices in the set and one had m vertices in the set. So in this situation, the total number of vertices was n plus m in the complete bipartite graph. And then we talked about this previously, the total number of edges was where if you multiplied those two guys together. Now, fun fact, this formula right here where the number of edges equaled n times n, I said that wrong, n times m, is actually using the formula where the sum of all the degrees equals two times the number of edges. You can actually apply that theorem, that formula that we've been using, onto your complete bipartite graph and actually recover right here this number of edges. Now, since we looked at it before, I just went ahead and gave you the formula again. Okay. Now, what I want to do here is illustrate another property of a bipartite graph that we haven't talked about yet, and it specifically deals with halves and circuits in your bipartite graph. So I'm going to look at the same graph twice. The first time we're going to find a path in the graph, and the second time is we're going to go ahead and we're going to find a circuit in the graph. And then we're going to extrapolate the property from there. So when finding the path, we can actually look at any path we want. So what vertex would you guys like to start at in terms of a path? And it doesn't matter. You guys have a preference. Sure. So we could start at 1. Now, if we start at 1, where would you guys like to go next? Note you only have two options. You can go to A or you can go to B. So which would I see? An A already came up. Now, once you're at A, you only have a couple of options, and your couple of options are 2. You have to go to 2. Now, if you're a path, you're not allowed to repeat edges or vertices. So when we're at 2, well, you can't go back to A. You have to go to B. Okay? And I'm going to go ahead, and when we go here to B, we could actually keep going. Do you guys want to keep going, or do you want to stop at B? Okay, so if we keep going, there's literally only one more place to be. So if we keep on going to, we could, in terms of B, the two possibilities of edges that haven't been used is either going towards 1 or to 3. But here, if we go to 3, we would actually pick up a circuit. Otherwise, if we go to 1, you have to pick up a circuit. If we go on to 3, it would be a proper path. Okay? Let's go ahead and go there to 3. So we found a path, and this one was 1 to A to 2 to B to 3, and this guy is a length 4 path. Now, you could also do other things. That's not the only path involved. See if I can erase the highlighter. I have a feeling I'm not going to be able to erase the highlighter. Ooh. No! Ah! That was what I was worried about. All right, so let's put the edges back in. Let's see. They're not so pretty anymore. Oh, well. Got this one, that one. Is that everybody? I think that was everybody we had. Now, that's not the only path. Yes. So the question is, for the length of the path, do you count the number of edges? And the answer is yes. So what that means is the length of the path is always one less than the number of vertices that you used. So suppose we picked on a different path, and for this one, maybe we picked on somebody like, oh, I don't know, maybe, I'm trying to get a different path. So maybe we started at 3, maybe we, well, at 3 you can only go to B. Maybe we then go to 1, and maybe we then go to A, and let's stop there. Okay. So in this particular case, that would be a different path. So 3 to B to 1 to A. And since it's a path, there's nothing in those directions that ask us to go and reach all of the vertices. Actually, if you do touch all your vertices, that's a special type of path that we'll look at later on. And this one here would then be what length, since we just talked about it. Yep, this would be a length 3 path. Okay. So notice what happened. We have options, paths of different lengths, and that's normal. Okay. So no change in terms of paths. Now, fun fact, suppose we take the exact same graph. Okay, so it's the same graph, just without any highlights. And suppose we now want to find a circuit. Now remember the deal with the circuit, this is where we want to start and end at the same thing. So we're going to try to, again, find a path, but instead of avoiding that first vertex, we're going to try to get back to the first vertex. Now here, again, it does not matter which vertex you start with. Let me go ahead and get it so I can do a highlighter, but maybe we start at A. I just did that because it was near the top. You could pick any vertex you want. Now once you're at A, where do you have to go? Well, you actually have a choice. You could go either to 1 or 2. Where would you guys like to go? Hint, it doesn't really matter. Well, I guess it will, and it'll depend on which circuit we actually pull. Sure, so we could go to 1. Now notice, in a bipartite graph, this first edge, whether you're dealing with just a path or whether you're dealing with a circuit where you have to come back to where you started, what happens? This edge is always going to shoot you over to a vertex in the other set of vertices. So here, if we title it, if this is like vertex set 1 or X, and this is like vertex set 2 or Y, what happens? If you start in X, next you'll go to Y. Where do we have to go once we're at vertex 1? So where should we go next? What's the next edge in this circuit we're trying to get to? Yeah, so this one, vertex 1 has degree 2. We can't go back to A because you can't reuse an edge in a circuit. So we have to come down here to B. Okay. Now once we're at B, we have some choices. We could go to 2 or we could go to 3. But remember, we're trying for a circuit, so we're trying to get back desperately to A. Now, because this is not a multi-graph, this second edge will never get you back to your starting point. So you're always going to have a situation here where you're going to come back to somebody else. Then your next edge is, in this case, it has to go to 2, so you have to go back the other set of vertices. And once we're at 2, can we actually get back to A like we wanted to? Can, which means we were able to find a circuit in the graph. And let's go ahead and write out that circuit. Okay, so we started at A, and first we went that way. So we have A, 1, we then went to B, we then went to 2, then we went back to A. And quick check, what's the length of this circuit, just since we've been talking about that? Yep, so this one would be 4 because we used 4 edges, or sometimes it's easier in a circuit because some people like to just ignore this last one because it's a duplicate of the first one. And in that case, if you ignore this last vertex, it would be like the unique vertices you visited. Some people like to think about it that way. I personally like to have less things to remember. So for me, it's one of the reasons I like having these little dashes instead of the standard commas, because you can literally just count up those dashes and it looks like edges. Okay. Now, you guys, when we were at B, you guys picked that we needed to go to 2. Anybody have a guess on why we couldn't have picked 3? What would have been the problem with going to vertex 3? Yeah, there's actually a couple of different problems, but the most obvious one with vertex 3 down here is once you go to vertex 3, you can't go anywhere else because it's degree 1. And you can't go anywhere else because you can't reuse your edges. So paths, totally cool when you're dealing with paths or matching to deal with your degree 1 vertices, but in circuits, you have to be with a circuit to get back to where you started. All of the vertices that you use actually turn out to have to be degree 2 or higher. Why would I say degree 2 or higher? The degree 2 allows for you to go in and out. Weird fact, but true. Actually, not that weird once you think about it. Now, so that's actually, regardless of whether it's bipartite or not, that's actually something that happens where you have to have the vertices or degree 2 or higher to get the circuit. But let's actually look at something specific to bipartite graphs, and it says the following. The specific to bipartite graph says, hey, so theorem 2, not the only theorem 2 in the book, but in this section, some graph G is bipartite. And this is actually another check for seeing if somebody's bipartite or not, if and only if every circuit in the graph has an even length. Now, it's perhaps easier to see this if you start with bipartite and then say, if you're a bipartite graph, then all your circuits are going to be even. So let's look at that direction first. So this is an example of a bipartite graph. Any guesses why your circuit would have to be even in a bipartite graph? I'm not going to lie, I kind of gave it away to you guys a little bit a second ago. Anybody have a guess? If you're a bipartite graph, why would all of your circuits have to have an even number of edges in them? Once you hear why, it's going to be super obvious. But getting to that why sometimes is, ooh, yes. So the answer is so you can go there and back again, roughly speaking. I know I paraphrased what you said. But yeah, so the thing here with the bipartite graph is you've got what? You've got all of your vertices are divided into 2 groups. Yes. So when you've got with your sides, you start on one side, your initial edge or any edge takes you to the other side. So in order to get back again, you have to have that at least that second edge to get back again. And notice they're going to come in pairs. So that means you had originally at least 2 sides. Well, in actuality, you have to have at least 4 because then you're like, oh, I didn't get back to A, so I have to go back to the other side, wherever you went, to then smallest circuit come back again. So in order to come back to whichever side you started with us, we called it vertex set X. We left vertex set X to come back. It takes 2 steps, which is summary of what many of you guys answered right there. So yes, that's actually why you've got this even length. Now, reverse that. Okay? If every single circuit in your graph has even length, remember, I think it was Friday when we did this, one of our ways to check to see if the 2 graphs were bipartite was what? We put a vertex on one side, and then we did all of the edges that were incidents to the vertex, and then we kept building, and we built up which vertices had to be on which vertex side, and which vertices had to be on the other vertex set or the other column. Well, it turns out if every circuit has even length, you'll automatically be able to force everybody into those 2 different spots. Now, what happens if you don't have every circuit has an even length? That odd length, that's when it guarantees that maybe you have a triangle shaped or a length 3 circuit. that would be where you would get the extra edge between two vertices on the same side. If you have a circuit of length 1, doesn't happen in simple graphs. If you have a circuit of length 5, same sort of idea. You go back and forth a couple of times, but then you've got one edge that stays on the same side. So this guy actually does work in both directions. So if you can find every single circuit in your graph has even length, that'll give you a bipartite graph. Not going to lie, that's not how it's normally used. Typically how this theorem is actually used is you find a circuit in your graph and say it has an odd length. That would immediately give you what conclusion? What do you guys think? If you found a circuit of, say, length 3, immediately you would know what? Exactly. You would immediately know that it's not a bipartite graph, and that's how this theorem is actually used a lot. So a way to show that somebody's not bipartite, but it can be used either direction. So let us look at an example. So suppose we have this graph right here. It looks like, well, a square inside of a square and then 2 extra edges. And we've seen a number of different examples that are similar to this. And I think I've got a second graph. Excellent. So this one here, if we start looking at the different circuits in this graph, notice there's a bunch of different ones. We actually have, if we started at E, we could go around the little square on the inside. Well, if you go around the little square on the inside, is that a circuit that has odd or even length? What do you guys think? Yeah, that would be even. Same deal if we picked any of the vertices on the outside, we could go all the way around the outside, and that would also have even length because we're looking at something that looks like a square. Now, what happens if we did this thing? So maybe we start at E, and then we went E to F to G to C to B to A back to E. What do you think? Is this guy, that sort of weird-looking shape, would that be a circuit that's even or odd? All right, so I've got 2 votes. Oh, more ones. Yep, so that one's actually even. So what was that, 6 edges if I'm counting correctly? 1, 2, yeah, 6 edges. So that one still actually is an even cycle. So far, everything we've done so far indicates that we've got circuits, all the circuits we've checked so far have an even length. Now, here's the only downside of trying to check all your circuits. If you try to check all your circuits and maybe you miss one, and maybe the one that you've missed is actually the one circuit in the graph that's odd. So if you start getting a lot of circuits and all of them seem to be even, it's pretty likely that this thing is bipartite, but let's go ahead and check using the technique that we know works. Oops, apparently I cannot draw right now. Just a second. So our technique, remember, that we know works in terms of checking to see if graphs are bipartite, is you go ahead and you pick one of your vertices, doesn't matter which one, and then you see what edge or what vertices that guy is incident to, and you list them all out on the other side. So A is incident to B, A is incident to, was that E? A is incident to D. Okay? So let's mark the ones we've done. That way we don't accidentally deal with the same vertex more than once. So we just dealt with A, and we also, I'll go ahead and just mark these guys. We've dealt with those guys so far. Okay? So, and we need to go ahead and put in the actual edges. So then if we go and look at, you got to look at some vertex that's currently in the graph that you're building. So maybe look at B. I like to start at the top and work down. So B is supposed to be incident to A. Check, got it. B is also incident to C. And notice B is degree 2. So that takes care of everything that is going to touch B. Then you can look at either any of these 3 guys that are left. So we've got C, E, or D. Oh, I don't know. Maybe we want to do, how about C next, just because I'm already here. So if we look at C, C has degree 3, so that means that C is incident to B, check. C is incident to D, check. And C is incident to G. So we'll put G in because we didn't have them yet. Now, go over to the other side because we've dealt with everybody on the left-hand side. E. E has degree 3, so it should be incident to 3 edges or adjacent to 3 vertices. E is adjacent to A, check. E is adjacent to who else? F and G. Excuse me, F and H. Ah! And that takes care of E. So next we need to deal with D. D is supposed to have degree 2, so D is done. F has degree 2, so we just need to figure out the one extra edge and we'll be done with F. So F is connected to or adjacent to E and G. E we got, G we put in. So now we just need to worry about the bottom two vertices. So it looks like it's screwed up somewhere. Let's see. E. That is embarrassing. That's because this last one was, oh, that last E is not an E. Anybody got what letter it should have been? Yeah. All right. Watch out for your typos because they will totally mess with you. As you can see, everybody does it at least once in their life and typically way more times. So we've got H, we've got G. G has degree 3, so there's one more edge dealing with G. And H has degree 2. There should be actually only one more edge to put in. Anybody spot what edge we're missing? It looks like it's the one that connects H to G. Yep, awesome. All right, so what does this tell us? Since we were able to draw the graph in the bipartite format or the two-column, or if you preferred two-row format, this tells you that this graph is bipartite. Wow, that is not how you spell bipartite. You need the BI in front, so let's fix that. Bipartite. Not a question. All right, so in terms of this guy, all of the circuits that we found were even. We didn't actually find all of the circuits, but once you get the majority of the circuits that you see are even, that tells you there is an extraordinarily high likelihood of the thing being bipartite, and that's when you go and do the check that we've seen before. Now, what happens if you have a slightly smaller graph? So suppose you have this guy, which is just a hair smaller, doesn't have quite so many vertices, it still looks like it has a few edges, but not quite so many there. Okay? If you look at this one, what do you think? Is that graph bipartite or not? Ooh, yes. So this one here totally has an odd circuit in it, and there's actually a bunch of odd circuits. So the one that I saw the most, and it looks like a couple of you guys were looking at some of these guys too, I'm seeing triangles everywhere. The triangle that I tagged in on, and I don't know why I looked at this triangle as opposed to any of the other triangles, although you can totally look at tons of other triangles, including the really big ones in here as well, or the non-triangle length 5 one right over there as well. When I was looking at it, that was the first one that I saw. So this one here is we have an odd circuit. And our odd circuit was 2, 6, 5, back to 2. Or go around the other way or start with a different vertex. This guy is length 3, or you could have just written, there is a length 3 circuit, and here it is. And what does that mean? This means this guy is not bipartite, and this is how that theorem is. I think I just doubled up some syllables there. Bipartite. Not bipartite, and this is us applying theorem 2. So that's how this theorem is typically used a lot. It's a really quick way of saying, hey, this guy is not bipartite. Look, I just spotted a circuit, and you guys shouted out several other circuits too. Okay. So, questions? Make sense? Feeling okay so far? All right. Well, that's it for section 1.3. Notice a lot of it was about the edges that were going on, hence the title Edge Counting, but there was also the little bit extra thrown in there about the components and then the bipartite stuff at the end. I'm not sure why your author doesn't combine everything about bipartite graphs together, but he doesn't think it's spaced out like matching was earlier, and how to find if somebody's bipartite, and then this one, how to find somebody's not bipartite. All right, so that's it for section 1.3. So the rest of today, we'll start looking at the topics in section 1.4. Section 1.4 is an extraordinarily important section. I don't think I told you this at the time, but section 1.2 is also extraordinarily important. Being able to figure out if two graphs are isomorphic, really important thing to do that we do all the time in graph theory. And the other thing is dealing with planar graphs. Why planar graphs? Because they're our nice type of graphs. Not that you have to have them, but they are a very nice type of graph. Okay? So first of all, let's go ahead and talk about what a planar graph is, and then we'll move on to some different examples and some of the stuff we get to do with them. Okay? So a planar graph is simply a graph. So you've got a vertex set, you've got an edge set, where you can redraw where you've drawn the vertices on your piece of paper so that none of the edges cross. Now, we've done this in the past. We've also had a lot of graphs so far where the edges didn't cross. For example, this guy right here would be a planar, would be a graph where we've drawn it such that none of the edges cross. Up here, these are two different picture representations for the same graph. So if you were given them independently, you might say, hey, these two guys are isomorphic to each other. But notice the first version that I wrote out here in this more red color, that's where the edges don't cross. But when we check to see if the graph was bipartite and put it in the two-column format, notice the edges do cross. Okay? So when we talk about planar graphs, we're looking at graphs where you could redraw them so that none of the edges cross. Okay? So for example, I think I've got two examples prepped up here. This first guy is a planar graph. And let me go ahead and label these vertices. A, B, C, D, just went around the edges randomly there. What do you guys think? My claim is that this guy is a planar graph. Any guesses on what you could do to redraw it so that it actually doesn't have any of those edges crossing? Yeah, the easiest thing to do is this edge right here, A to C. C is degree 1, so that means it's pretty minimal to move them. Let's go ahead and just move C so it's on the other side of A. So in this one here, I'm just going to leave A, B, and D alone. So here's A, there's D, there's B. I know it's smaller picture, but that happened. We just pulled C to the other side. Meant to have point or vertex C closer to A, but it didn't happen. Send B. Yep, that would be another way to do it. So another way to redraw this graph is you could also go ahead and do something like this. So again, keep A the same. Keep vertex C, roughly speaking, the same. And this one, our B and our D, are going to get extended a little bit, and I curved that line just to make sure there was no intersection. Technically speaking, you can curve lines, but we try not to in graphs. Okay. So notice there were a couple of different ways that we could redraw the given graph to get a graph where no lines cross, and both of them are perfectly fine. Notice in terms of these symbols, I went ahead and put that same symbol that says isomorphic. I could have also put the equal symbol here because we kept the vertices named exactly the same. We just physically drew it on the piece of paper differently. All right, so if we now look at this second example that looks like a box with an X inside of it or a square with both of its diagonals, what do you guys think? Does it look like this one might be able to be redrawn so that none of the edges cross? And it looks like there's several guesses already. Move C to the middle. Yes, that would totally work. So if we go ahead and draw A, make B and D a little bit bigger or a little bit further away from A, we'll move C to the middle right here. So we still have the edge AB, you still have the edge BC, you still have the edge CD, we still have the edge AD, so that's where the original square went, and the two diagonals, or the original two X's, AC we still have, and BD now looks like an outer edge. Okay. So those two are also two graphs that are isomorphic, or technically, since we didn't move the names or change the names of the vertices, you could also call these guys equal to each other. But regardless of the two ways here, one is drawn where the first way, where you have what looks like a square, is drawn so that the edges cross, and the second way, which looks like you're inside of a triangle, is where the edges don't cross. Okay? So that means this graph right here, the original two graphs, are planar graphs, both of them. Now, yes, so nope. So there is a distinction of the before and the after, and it's a different word than planar. All 5 of these pictures are considered planar graphs. The ones even with the edges crossing are still called planar graphs, but you don't use them in this format, so you would want to redraw them so that the edges don't cross. Once you've redrawn them, so all of these pictures in black, those guys are called plane graphs. So plane graph, notice it doesn't have the planar, it doesn't have the AR on the end, it just has the word, just the plane part. This one here is when you've redrawn your graph so that there are no crossing edges. So actually, let me go ahead and write that in here. So this is the time. So this is the graph with no crossing edges. Do I need to do any background? And just as a heads up, if it helps to remember this, the word plane in math is the formal term for you were able to draw it on a flat piece of paper. So a plane is like the same thing if when we talk about an XY coordinate plane, it's that flat two-dimensional surface. Now, there are graphs that are not planar. So there are graphs that there's no way that you can draw them so that the edges don't cross if you're drawing them on a flat piece of paper. There's something, and I don't think your book talks about this, there's something called a genus. A genus talks about whether you're actually going to be drawing something on what would look like a flat piece of paper, or if you're going to be drawing on something that looks different. So for example, one of your homework questions, and I have forgotten how soon it is that you're going to need to worry about this, it might actually be this section, is something called a torus. And a torus is a fancy word for essentially a donut shape. Pretend that looks like a donut. Okay? That's my attempt at a donut shaped. Okay? In this particular case, this guy would have what's known as genus 1. Genus, the way it was originally described to me, and I thought this was just a great way to remember it, was the number of holes that your shape has been punched into. That's terrible ways of phrasing it, though. It's the number of holes you have in your shape. So a torus is, you would look at the surface area of a torus, which would be what you draw on, but this actual figure has one hole in the middle here. So this actually has genus 1. A flat piece of paper has no holes in it, so it has genus 0. And planar graphs are graphs that can be drawn on some surface of genus 0. There's also something called a double torus. It's somebody that looks like a torus, but it really looks more like a 3D figure 8. So it would have actually 2 holes punched in it, and it would have genus 2. And if you're interested in these type of things, I've got a link. I believe it's at the bottom of your homework question assignments out of the textbook, because one of your homework questions talks about a torus. It actually has a link of these guys all nice and computer generated. But on something like this, you could actually draw a graph that would not be a planar graph, but on the torus, you can actually draw it so that the lines don't cross. And the trick would be something like this. You'd actually have an edge that would go around and then coming back. Okay. Now, technically, we don't really want to talk multi-graph here, but you do this and come back to some other edge. Okay. But we're going to ignore that, so all that was extra information for now. The thing we care about right now is planar graphs. That's something that you can draw on a piece of paper where there is no crossing edges. Now, let us look at a slightly more complicated example. Suppose we have this guy right here. Okay. So this is the graph. It's got 6 vertices and a bunch of edges. Okay. And what we want to know, and I forgot to write down the directions here, what we would like to know is this graph planar? Let me go ahead and write in the directions. So is graph, oh, let's go ahead and name it, graph G, a planar graph. Now, it turns out There's a bunch of different ways of whether you can determine whether a graph is planar or not. But in terms of what we've done so far, everything we've talked about so far is literally just seeing if you can move the vertices around so that when you move the vertices around and all the edges that are incident that vertex follows it, you can get it so the edges don't cross. Anybody have a guess of whether this graph might be planar or not? Not asking you what to do yet, but any guesses of whether it might be planar? Definitely more edges for sure. Ooh, I got a couple of guesses for not planar. Turns out it is much harder to show that somebody is not planar than to be able to redraw it. And so we're actually going to have a technique where you can get verifiable answers of whether the graph is planar or not. But before we jump into that, we want to do two things. And the first thing is, let's finish this example, and the second thing is talk about the dual of a graph. So first of all, let's go ahead and finish this one, and I'm going to claim that this one can be redrawn. And the way that I want to redraw this guy goes as follows. I don't want to do anything with vertices A, B, D, or I'll change F a little bit, but let me go ahead and highlight these guys. These guys, A, B, D, and F, we're going to roughly speaking keep in the same spot, but I want to move those two vertices, E and C, in, and I realize, ooh, I see two guesses here. Let's see, C and E, yes, that's the one that I was thinking of doing. I've got D and B. D, close to B, and F, that looks like that would work too. And the last one guess is D and C, D and C. That would untwist part of it, and E and F up. You might have to do something slightly different with the E and the F, but swapping these two looks like it may actually help as well. I'm not going to do all of those guesses that you guys sent in, but I'm going to do a couple of them. So what I'm going to do is I'm going to go ahead and I'm going to keep the non-highlighted vertices, roughly speaking, in the same location. So A, roughly speaking, stays the same. B, roughly speaking, stays the same. D, roughly speaking, stays the same. And F, I'm going to move F down just a hair, but I'm still going to keep it roughly in the same spot. Okay? So let me draw in all of the edges that go with these four vertices first, and then we'll deal with E and C. So A is adjacent to B, A is adjacent to C, which we haven't drawn yet, E, which we haven't drawn yet, A is adjacent to D, B is adjacent to F and A. It's also adjacent to C, which we haven't drawn in yet, and adjacent to D. F is only adjacent to B and D, and D is adjacent to A, B, F, and C. So we've drawn in everything that we can so far. Now, in terms of what we need to do next, this is how you start looking at if you want to try doing this all by hand. C here needed to be adjacent to who? It needed to be adjacent to E, A, B, and D. So if you need to be adjacent to A, B, D, and the undrawn E, you need to be inside of this triangle so none of the edges cross any of the three edges A, B, B, D, or A, D. So I'm going to go ahead and draw C inside of this triangle. Now if C is drawn inside of that triangle, E is also going to have to be drawn inside of that triangle. So let's go ahead and put in the edges incident to C. So C is adjacent to A, B, D, and E, which is not yet drawn. Now, E is adjacent only to A and C, so E needs to be put in the triangle ACD or the triangle ABC. Either one would work. I'm going to put in the bigger one. So here's E, and then put in those extra two edges, and that should have redrawn the graph. So notice here, it is not always obvious if your graph is going to be planar or not from first guess. You might have to do a little bit of work here. And one of the ways that I find extremely helpful to check planar is I think of this as something that you can physically manipulate. Like maybe these vertices are actual things you can touch. Maybe these edges are something like rubber bands between whatever you're picturing the vertices to be, and you can actually move these vertices around. I think of it in terms of the edges. I think of it in terms of untwisting those overlapping edges, but that's not helpful for everybody. Okay? So the conclusion here goes as follows. The first graph would be planar. So G is planar. But is this first graph that's in red, is it a plane graph? What do you guys think? Is this first one a plane graph? And the answer is what you guys have been sending in, which is no, because you still have edges that are crossing. So it's planar, but not a plane graph. Now, when we look at this other guy, this one is also a planar graph, but is it also a plane graph? And the answer now would be yes, as several of you guys are saying. You're correct. So it's both planar and a plane graph, and that is because we now don't have any of those crossing edges. So yes, there is a terminology change when you go from the graph that has the crossing edges to its form where you don't have the crossing edges, and that's whether you use this term plane graph or so plane graph or not a plane graph. But the buzzword planar is any graph that's isomorphic to a graph that has no edges that are crossing. Now, let us end on talking about the definition of a dual, and then next time we'll get to an algorithm or method that'll determine whether a graph, regardless of how complicated it is, whether it is a planar graph or not. To be fair, it doesn't work for all graphs, but it does work for quite a lot of them. So if we look at the definition of a dual graph, the definition of a dual graph or a dual of a graph only works on planar graphs. Now, it can be a planar multigraph, which I'll be honest, we didn't define yet, but you guys now know the definition of a planar graph. Any guesses what a planar multigraph might be? Don't overthink it. Still, the edges shouldn't cross if you drew it in its plane graph form, but now it's okay if you have multi-edges. So that's the only difference, okay? So this is, you got a planar graph, given some planar graph, the dual or its dual is a graph, and its dual is almost always a multi-graph if you started with a simple graph, okay? So its dual is a multi-graph or a graph that has a vertex in place of each face of the graph, and we'll define a face here in just a second, and an edge wherever two faces of the graph are separated by an edge. Okay? Now, it's easiest to define a face by a picture. There are two types of faces. The easiest to spot is somebody called a bounded face. A bounded face is literally this guy. This would be an example of a bounded face. It's the space that the circuit is containing. So it literally is, you're looking at circuits. So this guy, a bounded face, is a circuit. And specifically, you're looking at the region that is contained by the circuit. In other words, one of the ways that I've thought about it in the past is you're looking for little polygonal shapes. That doesn't work in all cases, but it's like a nice first thought. Okay? Now, most of your faces in a planar graph are going to be bounded. In fact, all of your faces except for one are going to be bounded. So let us look now at an unbounded face. An unbounded face looks like this. Again, you have a circuit, and maybe you have some face that's inside your circuit. Okay, so that would be the bounded face. The unbounded face is the part here outside of the circuit. Okay? There's exactly one unbounded face in your graph. Note, one. Don't put the word B, letter B, because we need unbounded face. And often, people call this one F with a little infinity symbol at the bottom. That was totally trying to be an infinity symbol down there in the subscript. Why infinity for unbounded? Okay. Now, let us see how this would work. I think we can go ahead and look at examples. So if we look at, and let me make sure you can see this. So if we look at some example graph, for example, this guy right here, first check is, let's look to see, oh, question. Yes. So in this first example up here, the bounded face would be the shaded region. The unbounded face would be the part that would be outside of the triangular region. So yes, that would be correct. Now just to make sure we're all comfortable with our faces, vertices, etc., if we look at this example right here, I'm going to up here, how about over to the side? If we look at the number of vertices, how many vertices and edges do you think are in that graph? Anybody get that count? Yep, it looks like 6 vertices. Anybody spot how many edges there are? I'm counting 8. All right, you guys are too. Awesome. Now, anybody spot how many faces there are? Almost. So there are face 1, and let me go ahead and label it, face 2, and face 3. So we have 3 bounded faces. So add 1 for the unbounded face, which is out here, and you have a grand total of 4 faces. Okay. Watch out, your book talks about something completely bizarre and stupid with respect to duals. Please, please don't listen to your book when it talks about duals, at least in how to create them. Okay. He does some really weird things and creates something that nobody really uses as a dual. Formulas are fine. So if we want to actually create a dual here, here's how you do it. What did we say in terms of our definition? It said everywhere there was a face in the graph, in the dual, we're going to turn that face into a vertex. So everybody draws the dual on top of your original graph. If you're doing this on your own piece of paper, I would definitely recommend when you do this later on to go ahead and draw your original graph either in ink or in something that's a different color. So it's easy to tell who your original graph was. Then if you want to redraw your graph in a separate little spot, totally cool. So what you do, regardless of whether you name them or not, you put a vertex in the middle of each space. So inside of that 4 circuits, so inside the thing that looks like a square, inside of each of the 3 circuits, so inside of each of the guys that looks like triangles, and then 1 totally outside of your graph totally, and that one's going to represent your unbounded edge. Now, the next thing that we're going to do is we're going to put in the new edges for your graph. So the dual of your planar graph, each edge occurs anywhere 2 faces of your graph are separated by an edge in the original graph. So here's how you deal with this in the original graph here. People tend to put dotted lines in case you don't have different colored ink. So here, notice there is an edge, the edge CE, between the face labeled as F2 and the unbounded face. So I'm going to go ahead and put a dotted line there. That dotted line is going to represent our edge in the dual. I'm just going to do dotted lines everywhere because that's standard. Now, we also have face 3 down here. We can put in this another dotted edge between F3 and the unbounded edge. Notice it crosses right here, the edge EF. We can also put in another edge, do the same thing up here at the top of the graph, put in an edge between this face F1, the vertex there actually, and your unbounded face. Now, here's the question. Are there more edges in the dual graph? Do you think we need to include more dotted lines? The answer is yes. It turns out there's actually 5 more. Anybody spot another edge? DE. Can I assume you mean the edge that's going to cross DE? Okay. Yep, we've got an edge that'll go between F1 and F2. That would be crossing BC. We also have an edge between F2 and F3, and that would be crossing DE. Okay? So notice all of these dotted edges are literally intersecting an edge you have in the original graph. I'm seeing 3 more. Can I assume that means the edges that you're trying to cross? It looks like it from context. So if we look down here, F3, because that's where my cursor was, this one here, this F3, this face 3, or what's going to turn into a vertex in the dual, there's no edge right now that's going over the original edge DF. I'm going to go ahead and make this guy cross that edge, and notice where does it have to end up? this guy has to go and end up back at the unbounded face over there. Same deal with the next two edges down here in the one that was represented by this 4 circuit, or the guy that was a square. We haven't yet had a dotted edge that crosses the edge BD, so we'll go ahead and do that. And this edge needs to go and grab our unbounded edge. Same deal, last guy, the edge AB hasn't been crossed yet. So here, F1, we're going to go ahead and make that last line from F1 to F infinity, or the unbounded edge, by crossing this edge right here. Now, notice what that actually means. When you are now in the dual, and we can do this without doing anything else in terms of redrawing this dual, although I will here in just a second. Any guesses how many edges are in the dual as relates to the number of edges in the original graph? Same number, bigger, smaller, any guesses? And as you guys are guessing, I'll go ahead and start redrawing this guy. It turns out, as I see no more guesses coming through, it turns out it's always going to be the same. So here we should have had 8 edges. Any guesses why it's always the same? Oh, I see no guesses. It's always the same because notice how you found these dual edges. You had to go and cross an edge that you already have. Yep, there the answer came in. So because you always cross an edge you already have, and it's exactly once, you'll get the same number of edges. Notice here the number of vertices is going to match the number of faces that you originally had because we converted all faces into vertices. Now, one last check and then we're going to be done. Anybody have a guess how many faces are in the dual? Well, let's count them up. Oh, you've got a guess for 6. It turns out that is correct. We've got 1, 2, 3. So those weird ones with them formed by the multi-edges. There's 3. 4, 5. So ones that look like proper faces. And then don't forget the unbounded edge. So there's the 6th one. So as a lot of people like to say, 5 for bounded plus 1 to give you your unbounded. Okay. No, anybody notice correlation between these numbers, the 6, the 8, the 4, and the 4, the 8, the 6? Hopefully you're all thinking to yourselves, yeah, the order reversed. Edges always stay the same, but the number of faces and the number of vertices will flip-flop between your original and your dual. And that's true all the time, just based on how this works. The dual only works on planar graphs, and for planar graphs, this will always work. It also always works for planar multigraphs. Notice we automatically here formed a planar multigraph. Multigraph because there's some multi-edges, planar because you can still draw it with no crossing edges. But that is definitely it for today. Next time, we'll get into dealing with how to recognize if your graph is planar or not, especially if there's tons and tons of edges, and we'll actually have 2 main strategies, one of which works the majority of the time, and the other one works all the time, but is a little bit more difficult to deal with. But that is it for today, unless you guys go ahead and have any questions. Or I guess, unless you guys have any questions.